Most people assume the moon has always been exactly where it is now, locked in an eternal dance at its current distance. We picture it as Earth's faithful companion, steady and unchanging across the eons. But this assumption is completely wrong. The moon is not staying put, it's leaving us. When dinosaurs ruled the Earth 100 million years ago, the moon loomed 25% larger in the sky. A day lasted only 23 hours because Earth spun faster. The tides were monstrous, ocean waves that could swallow entire coastlines twice a day. Go back even further, to when life first emerged in Earth's oceans 3.8 billion years ago, and the moon appeared 3 times larger than it does today. It hung in the sky like a second sun, creating tidal forces so extreme they may have helped spark life itself. But here's what makes this deeply unsettling. This process will never stop. The moon will continue its relentless retreat for billions of years until something fundamental breaks in the Earth-Moon system. In 600 million years, total solar eclipses will become impossible because the moon will appear too small to cover the sun. In 50 billion years, if Earth still exists, the moon will be so distant that a month will last 47 current days, and Earth will show the same face to the moon forever, just as the moon currently shows us only one face. This isn't just astronomical trivia. The moon's gradual departure is reshaping our planet in ways most people never consider. It's slowing Earth's rotation, lengthening our days, and fundamentally altering the nature of time itself on our world. Climate patterns, ocean currents, and even the stability of Earth's axis depend on the moon's gravitational influence, an influence that weakens with every passing century. Scientists discovered this lunar retreat through a method so precise it borders on science fiction. Since 1969, astronauts have placed special mirrors on the moon's surface. Observatories on Earth fire laser pulses at these mirrors and measure how long the light takes to return, accurate to within a few millimeters. Month after month, year after year, those measurements reveal the moon steadily receding into the cosmic darkness. The mechanism driving this escape involves forces most people misunderstand completely. It's not that gravity is weakening or that some external force is pulling the moon away. The culprit is something far more subtle and beautiful. The very tides that create peaceful waves on Earth's beaches are gradually stealing rotational energy from our planet and transferring it to the moon's orbit. Every tide that rises and falls is participating in this 4.5 billion year cosmic conspiracy. Tonight, we're going to explore one of the most profound ongoing changes in our solar system. A change so slow it's invisible to human perception, yet so consequential it will determine the ultimate fate of Earth itself. We'll discover why the moon formed much closer than most people realize, how ancient coral reefs preserve evidence of shorter days from 400 million years ago, and why this seemingly gradual process actually unfolds in distinct phases with dramatically different consequences. You'll learn why the moon's retreat is simultaneously weakening Earth's magnetic field, destabilizing our climate, and setting up our planet for a future that will be almost unrecognizable. We'll explore what happened to other moons in our solar system that underwent similar migrations, and why some never made it to safety. By the end of this journey, you'll understand why every sunrise happens slightly later than it would if the moon stood still. Why ancient astronomers recorded eclipses that lasted longer than any eclipse possible today, and how this gradual celestial divorce will eventually reshape everything from the length of seasons to the behavior of Earth's core. If you're fascinated by cosmic processes that unfold on timescales beyond human comprehension, subscribe and hit the thumbs up button. And here is a question I want you to consider. If you could control the moon's distance from Earth, where would you place it for the most interesting consequences? Comment below with your reasoning. I'll pin the most scientifically creative answer. The story of the moon's mass retreat connects nuclear physics happening inside our planet to gravitational dynamics playing out across billions of years. It reveals how the cosmos operates like a vast clockwork mechanism, where every motion influences every other motion in an endless cascade of consequences. This is simultaneously one of the most predictable and most transformative processes in our corner of the universe. Now, let's begin our journey into the mechanics of cosmic separation, starting with a simple question that has a surprisingly complex answer. What exactly is pushing the moon away from us? Chapter 1. Tidal forces. The moon isn't being pushed away from Earth by any external force. Instead, it's being dragged away by something happening right here on our planet every single day: the rise and fall of the tides. But the mechanism behind this cosmic tug-of-war operates in ways that challenge most people's intuition about how gravity and motion work in space. When you think of tides, you probably picture water sloshing back and forth in Earth's oceans. The basic explanation you learned in school suggests that the moon's gravity pulls water toward it, creating a bulge on the side of Earth facing the moon. This is partially correct, but it's only half the story. The complete picture reveals why tides are actually stealing energy from Earth's rotation and giving it to the moon's orbit. Here's what's really happening. Earth isn't just experiencing one tidal bulge pointing toward the moon. It's experiencing two bulges on opposite sides of the planet. The bulge facing the moon forms because lunar gravity is stronger on that side of Earth. Water gets pulled toward the moon more powerfully than Earth's center does. But the bulge on the opposite side forms for a more subtle reason. That side of Earth experiences weaker lunar gravity than Earth's center, so it effectively gets left behind as the planet falls toward the moon. Picture Earth as a flexible rubber ball being squeezed by invisible hands. The moon's gravity creates this squeezing effect, stretching our planet into a slightly oval shape. The solid Earth deforms by about 50 centimeters twice daily. Your house literally rises and falls by half, a meter every 12 hours, though you never notice because everything around you moves together. But here's where the energy transfer begins. Earth rotates faster than the moon orbits. Our planet spins once every 24 hours, while the moon takes 27.3 days to complete one orbit. This means Earth's tidal bulges are constantly trying to race ahead of the moon. As the planet rotates, it attempts to drag those two water bulges along with it. The moon's gravity fights back, trying to keep the bulges aligned with its position. This creates friction, not mechanical friction like car brakes, but gravitational friction as Earth's rotation works against the moon's gravitational pull. The ocean floors experience this as a constant drag, and rocky continents plow through the tidal bulges like ships moving through water. This friction has profound consequences. Every time a tide rises and falls, it's converting some of Earth's rotational energy into heat. That energy gets dissipated through turbulence in shallow seas, friction against continental shelves, and the internal flexing of Earth's crust. Scientists estimate that Earth loses about 3.7 terawatts of rotational energy this way, equivalent to the power output of 3,700 nuclear reactors running continuously. But energy cannot be destroyed, only transferred. Where does Earth's lost rotational energy go? Directly into the moon's orbital motion. As Earth spins down, the moon speeds up in its orbit. And here's the counterintuitive part. When an object in orbit gains energy, it actually moves to a higher, more distant orbit. This is exactly opposite to what happens with everyday objects. If you throw a ball harder, it goes farther because it has more energy. But in orbital mechanics, more energy means more distance from the central body. The moon gains approximately 3.8 centimeters of orbital distance each year through this process. That might sound insignificant, but consider the accumulated effect over geological time. Since life first appeared in Earth's oceans, the moon has retreated by thousands of kilometers. When complex life began evolving 500 million years ago, the moon was 20,000 kilometers closer than it is today. NASA's Lunar Laser Ranging Experiment, conducted since 1969, measures this retreat with extraordinary precision. Astronauts from Apollo 11, 14, and 15 placed retroreflectors, special mirrors designed to bounce laser light directly back to its source on the moon's surface. Ground-based observatories fire laser pulses at these mirrors and measure the round-trip travel time. The measurements are accurate to within 3 centimeters across the 384,400 kilometer distance to the moon. These measurements reveal something remarkable. The moon's retreat rate isn't constant. It varies slightly due to changes in Earth's tidal patterns, the distribution of continents, and even the amount of ice stored in polar regions. During ice ages, when sea levels drop, tidal friction decreases and the moon retreats more slowly. When ice sheets melt and sea levels rise, the process accelerates. The most dramatic variations occurred during major geological transitions. When the supercontinent Pangaea began breaking apart 200 million years ago, it completely restructured Earth's ocean basins and tidal patterns. The moon's retreat rate during that period may have been double or triple the current rate, as new shallow seas formed and generated enormous tidal friction. To put this energy transfer in perspective, imagine Earth as a spinning figure skater pulling her arms inward to spin faster. The tidal process is like that skater gradually extending her arms, slowing her rotation while gaining energy in other ways. Except in Earth's case, the extending arms is the moon moving farther away, and the process has been continuing for over 4 billion years. Modern computer models can recreate this process across deep time. Dr. Hannah Davies at GFZ Potsdam published research in 2020 showing that 2.5 billion years ago, when Earth's day was only 17 hours long, the moon was creating tides over 1,000 meters high. The gravitational stress on Earth's crust was so intense it may have influenced the formation of mountain ranges and the movement of continents. The implications ripple through every aspect of Earth's behavior. As the moon retreats and Earth's rotation slows, our planet becomes less efficient at generating its magnetic field. The magnetic field depends on rapid rotation of Earth's molten iron core, and even small changes in rotation rate can weaken magnetic protection against solar radiation. This sets up a feedback loop that will define Earth's far future. Weaker magnetic fields allow more solar wind to strip away atmospheric particles. A thinner atmosphere changes climate patterns, which affects ocean circulation and tidal patterns, which influences the rate of the moon's retreat. Every component of the Earth-Moon system is connected to every other component in ways that compound over millions of years. But the story becomes even more complex when you realize that Earth isn't the only world experiencing this process. Throughout the solar system, moons are either spiraling inward toward their parent planets or spiraling outward away from them, depending on their orbital characteristics and their planet's rotation rate. The moon's outward migration is just one example of a universal gravitational choreography that has been reshaping planetary systems since the cosmos began. Understanding tidal forces as the engine of lunar retreat opens the door to a deeper question. If this process has been going on for billions of years, what did the Earth-Moon system look like when it first formed? The answer will fundamentally change how you think about the early history of our world. Chapter 2. Ancient Proximity. When the moon first formed 4.5 billion years ago, it hung in Earth's sky like a colossal sentinel, appearing 15 to 20 times larger than the moon we see today. The infant moon orbited at just 22,000 kilometers above Earth's surface, closer than most communication satellites orbit now. From Earth's surface, this primordial moon would have filled roughly 40 degrees of the sky, appearing as a massive, roiling ball of molten rock that dominated both day and night. The leading theory for the moon's formation, known as the giant impact hypothesis, suggests our satellite was born from cosmic violence on an almost incomprehensible scale. About 50 million years after Earth formed, a Mars-sized object called Theia collided with the young Earth at a glancing blow. The impact vaporized both objects' outer layers, ejecting massive amounts of material into orbit around Earth. This debris disk gradually coalesced into the Moon over a period of several thousand years. Dr. Robin Canup at the Southwest Research Institute has run detailed computer simulations of this formation process. Her models show that immediately after formation, the Moon would have been so close to Earth that gravitational forces nearly tore it apart. The Roche limit, the distance at which tidal forces overcome an object's gravity, was perilously close to the Moon's initial orbital distance. Only the Moon's relatively large size and rapid orbital motion saved it from being shredded into a ring system. At this ancient proximity, the Moon appeared to move visibly across the sky, where today, the Moon takes about 2 minutes to move its own diameter against the background stars. The primordial Moon would have raced across the heavens, completing one orbit around Earth in just 5 to 6 hours. Imagine watching a Moon 20 times larger than today, as rushing from horizon to horizon several times each day, its molten surface glowing like a second sun. The tidal forces generated by this close Moon were beyond anything we can directly compare to modern experience. Earth's oceans, if they had existed then, would have experienced tides over 3 kilometers high, waves that could have submerged most mountain ranges. But Earth in this era had no oceans. Instead, the planet's surface was mostly molten rock, and the Moon's gravity raised tides in this liquid stone that reached heights of several kilometers. These rock tides created a feedback mechanism that determined the Moon's ultimate fate. Unlike water tides, which dissipate energy through friction and turbulence, rock tides dissipate energy through the internal heating and deformation of Earth's crust. The young Earth was much hotter and more molten than today, making these tidal interactions extremely efficient at transferring energy from Earth's rotation to the Moon's orbit. The physics of this early Earth-Moon system operated under extreme conditions that no longer exist anywhere in our solar system. Earth was rotating so rapidly that a day lasted only 5 to 6 hours. The planet was essentially a spinning ball of molten rock with a massive companion orbiting just outside the distance where tidal forces would destroy it. The gravitational interactions were so intense they may have influenced Earth's core formation and the differentiation of heavy elements toward the planet's center. Evidence for this ancient proximity comes from multiple sources, but one of the most compelling involves the composition of lunar rocks returned by Apollo missions. The Moon's overall density and the ratios of certain isotopes in lunar material match Earth's mantle composition almost exactly. This suggests the Moon formed from Earth material ejected during the giant impact, material that would have been in orbit very close to Earth's surface. Additionally, computer models of tidal evolution consistently point toward the same conclusion. When you run the physics backward from the Moon's current position and retreat rate, accounting for changes in Earth's rotation and tidal patterns over geological time, the calculations converge on a Moon that formed at roughly 22,000 kilometers distance from Earth's center, about 3.4 Earth radii. The retreat from this initial distance wasn't gradual and steady like today's migration. During the first 100 million years after formation, the Moon receded rapidly from Earth due to extremely efficient tidal energy dissipation. The molten or partially molten Earth provided much less resistance to tidal deformation than today's solid crust, allowing energy transfer to occur at rates perhaps 1,000 times faster than current levels. Dr. Jack Wisdom at MIT has calculated that the Moon likely reached a distance of 60,000 kilometers within the first 100 million years, roughly 15% of its current distance. This rapid early migration had profound consequences for Earth's development. As the Moon retreated and Earth's rotation slowed, the planet began to cool and solidify. The reduced tidal heating allowed Earth's surface to form a stable crust for the first time. The transition from rapid to gradual retreat occurred when Earth's surface solidified enough to support stable oceans. Once liquid water covered significant portions of Earth's surface, tidal energy dissipation shifted from rock deformation to ocean friction. This change dramatically slowed the moon's retreat rate and established a more gradual migration pattern that has continued for the past 4 billion years. Ancient evidence supports this picture of extreme early tidal forces. Some of the oldest rock formations on Earth, dating to 3.8 billion years ago, show patterns of rhythmic layering that may preserve records of these ancient tidal cycles. The banded iron formations in Greenland and Australia contain depositional patterns that occur at regular intervals, potentially reflecting tidal influences when Earth's day was much shorter and tidal forces much stronger. The early proximity also explains several puzzling features of the Earth-Moon system. The Moon's orbital plane is tilted 5 degrees relative to Earth's equator, which is unusual for a satellite that supposedly formed from Earth material. This tilt likely resulted from gravitational perturbations during the period of rapid early migration, when the Moon's orbit was still settling into its current configuration. Perhaps most importantly, the Moon's early proximity may have been essential for the development of life on Earth. The extreme tidal forces created by the close Moon would have generated massive circulation patterns in Earth's early oceans. These tidal currents could have concentrated organic molecules in tidal pools, provided energy for chemical reactions, and created the dynamic environments where the first self-replicating molecules might have emerged. Research published in 2018 by Dr. Abe Baritz at the University of Southern California suggests that the Moon's early proximity created a tidal resonance effect that amplified chemical evolution. The rapid day-night cycle, combined with extreme tidal mixing, would have subjected organic compounds to repeated cycles of concentration, dilution, heating, and cooling, exactly the conditions needed for complex molecular evolution. The retreat from ancient proximity also established Earth's unique rotational characteristics. Without the Moon's early gravitational influence, Earth might have ended up with a rotation period of only 8 to 10 hours, creating a very different climate system. The Moon's gradual retreat allowed Earth to settle into a 24-hour day that provides stable seasons and climate patterns suitable for complex life. This raises a profound question about planetary habitability. How many other worlds in the universe have experienced similar moon formation events that created the right conditions for life? The specific circumstances that led to the Moon's formation, a giant impact at just the right angle, creating a satellite at just the right distance around a planet of just the right size, may be much rarer than previously thought. Understanding the Moon's ancient proximity reveals that our satellite isn't just a passive companion that happens to orbit Earth. It is an active participant in Earth's evolution that has been shaping our planet's character for 4.5 billion years. But the story becomes even more remarkable when you examine the physical evidence that this process has left behind in Earth's geological record. Chapter 3. Geological Evidence. Hidden within layers of ancient rock lies a detailed record of the Moon's gradual retreat from Earth, preserved with the precision of a cosmic timekeeper. These geological archives don't just suggest that days were shorter and the Moon was closer in the past. They prove it with mathematical certainty, providing a timeline of Earth's changing relationship with its satellite that extends back over 500 million years. The most compelling evidence comes from an unexpected source: ancient coral reefs and the growth patterns they left behind. Corals grow by depositing calcium carbonate in daily layers, much like trees add annual rings. But corals also show monthly and yearly growth cycles, creating a natural calendar system that records the passage of time with remarkable accuracy. In 1963, paleontologist John Wells at Cornell University made a groundbreaking discovery while studying fossilized corals from the Devonian period, about 370 million years ago. He counted the daily growth ridges within the annual bands and found something impossible. These ancient corals showed approximately 400 days per year instead of 365. The implications were staggering. Either the ancient corals were completely wrong about how time worked, or Earth was spinning significantly faster in the Devonian period. Wells' discovery launched decades of research into what scientists now call cyclostratigraphy, the study of astronomical cycles preserved in rock layers. The evidence has grown overwhelming. Middle Devonian corals consistently show 395 to 400 days per year. Carboniferous corals from 300 million years ago show about 390 days per year. Early Jurassic specimens from 200 million years ago show 385 days per year. The pattern is unmistakable. The farther back in time you look, the shorter Earth's days become and the more days fit into a year. Since Earth's orbital period around the Sun has remained essentially constant, this can only mean that Earth rotation has been gradually slowing down. Exactly what tidal theory predicts. Dr. Judith Totman-Parrish at the University of Arizona expanded this research in the 1980s by studying banded limestone formations called tidal rhythmites. These rocks form in shallow marine environments where tidal currents repeatedly deposit and erode sediment layers. The thickness of individual layers reflects the strength of tidal currents, which varies in predictable cycles based on the Moon's orbital period and phases. Rhythmites from the Proterozoic era, over 600 million years ago, show tidal cycles that occurred every 19 to 20 hours instead of the current 24.8-hour lunar day cycle. This indicates not only that Earth was rotating faster, but that the Moon was orbiting much closer, creating stronger tidal forces with shorter periods between high tides. Perhaps the most precise evidence comes from formations in the Australian Flinders Ranges. Dr. George Williams from the University of Adelaide analyzed rhythmites there that date to 620 million years ago. The rock layers show daily, monthly, and annual cycles preserved with extraordinary clarity. His measurements revealed that Earth's day was 21.9 hours long, and the Moon completed one orbit in just 20.1 days, compared to today's 27.3 days. The mathematics is unambiguous. If the Moon orbited closer to Earth, it would orbit faster due to stronger gravitational acceleration. If Earth rotated faster, tidal cycles would occur more frequently. The geological record provides exactly the evidence you would expect from a Moon that was closer and faster, orbiting a planet that was spinning more rapidly. But corals and rhythmites aren't the only geological witnesses to the Moon's retreat. Laminated lake sediments called varves also preserve daily and seasonal cycles. The Green River Formation in Wyoming, dating to about 50 million years ago, shows annual varves containing approximately 377 daily layers. Even this relatively recent time frame shows Earth rotating noticeably faster than today. The evidence extends beyond just counting days and years. The strength of tidal forces recorded in ancient rocks tells us how close the Moon was at different times in Earth's history. When the Moon was closer, tidal ranges were more extreme, creating more dramatic patterns in tidal deposits. By analyzing the amplitude of tidal cycles preserved in rock, scientists can calculate the Moon's distance at the time those rocks formed. Research published in 2018 by Dr. Stephen Myers at the University of Wisconsin used astronomical analysis of rock formations to push this timeline much deeper into the past. His team studied 90 million-year-old rocks from Colorado and 1.4 billion-year-old rocks from northern China. The results confirmed that Earth's day length has been steadily increasing throughout geological time. The Chinese formations were particularly revealing. At 1.4 billion years ago, Earth's day was only 18.7 hours long, and the Moon was approximately 44,000 kilometers closer than its current position. This places the Moon at about 340,000 kilometers from Earth, roughly 89% of its current distance. The difference might seem small, but it represents a moon that appeared about 25% larger in the sky and generated tides roughly twice as powerful as today. Sus. These measurements also reveal something unexpected. The rate of the moon's retreat hasn't been constant over geological time. During certain periods, the moon retreated more rapidly due to favorable continental configurations that enhanced tidal friction. During other periods, the retreat slowed when continents were arranged in ways that reduced tidal energy dissipation. The most dramatic changes occurred during major continental breakup events. When Pangaea began fragmenting 200 million years ago, it created new ocean basins and shallow seas that dramatically increased global tidal friction. Geological evidence suggests the moon's retreat rate may have doubled during this period, before settling back to more normal rates as the new ocean basins matured. Modern deep-sea drilling projects have extended this research even further. The ocean drilling program has recovered sediment cores from ocean floors that preserve tidal cycles in their layering patterns. Cores from the Atlantic Ocean show clear evidence of changing tidal patterns as the basin widened and deepened over the past 180 million years. One of the most elegant confirmations comes from studying ancient solar eclipses recorded by human civilizations. Chinese astronomers documented solar eclipses as early as 2000 BCE, and these records can be compared to calculated eclipse paths based on current orbital mechanics. The ancient eclipse records consistently show slight discrepancies that match exactly what you would expect from a moon that was closer to Earth and a planet that was rotating slightly faster. Dr. Richard Stevenson at Durham University has analyzed over 2,000 historical eclipse records and found that Earth's rotation has slowed by approximately 2.3 milliseconds per day per century over the past 2,700 years. This rate matches perfectly with modern measurements of the moon's retreat and provides an independent confirmation of tidal evolution theory. The geological evidence also reveals the future trajectory of Earth-Moon evolution. By measuring how retreat rates have changed throughout geological history, scientists can model what will happen over the next billion years. The patterns preserved in ancient rocks serve as a calibration for computer models that predict Earth's far future. Perhaps most remarkably, some of the oldest evidence comes from formations nearly 3.8 billion years old. Banded iron formations in Western Australia contain rhythmic patterns that may preserve tidal cycles from when Earth's oceans first formed. If these interpretations are correct, they suggest that even in Earth's earliest oceans, the moon was already retreating at measurable rates. This geological archive represents one of the longest continuous records of any astronomical phenomenon. While human civilizations have existed for mere thousands of years, the rocks themselves have been faithfully recording the moon's migration for hundreds of millions of years. Each layer tells part of a story about gravitational forces operating across deep time, reshaping both Earth and its satellite through processes too slow for any individual observer to notice. The evidence locked in these ancient formations proves that the moon's retreat isn't a modern phenomenon or a recent discovery. It is a fundamental process that has been shaping Earth since shortly after our satellite formed. But this raises an intriguing question. What was life like on Earth during periods when the moon was significantly closer and more influential than today? Chapter 4. Shorter days. Imagine waking up on Earth 400 million years ago, during the Devonian period when our planet was a fundamentally different world. The sun rises after a night that lasted only 10.9 hours. You have exactly 11.1 hours of daylight before darkness returns. A complete day-night cycle takes just 22 hours instead of the 24 hours your body expects. This isn't science fiction. This is what Earth was actually like when the moon was closer and our planet spun faster. These shorter days created a world that would challenge every assumption you have about how planets work. The rapid rotation fundamentally altered Earth's weather patterns, ocean currents, and even the behavior of life itself. Species that evolved under 22-hour days developed biological rhythms completely different from anything alive today. The physics of faster rotation affected Earth in ways that compound and amplify each other. A planet spinning faster generates stronger centrifugal forces, making objects at the equator weigh slightly less than objects at the poles. On ancient Earth, this effect was more pronounced. A person standing at the equator would have weighed about 1% less than the same person at the North Pole, compared to just 0.5% difference today. More dramatically, faster rotation created more powerful Coriolis effects, the phenomenon that causes moving objects to curve due to Earth's rotation. Ancient Earth's stronger Coriolis forces would have generated weather patterns unlike anything we see today. Hurricane-like storms would have been smaller but more intense, and they would have rotated faster and followed different paths across the oceans. Dr. Norman Sleep at Stanford University has modeled these ancient atmospheric conditions using the same equations that govern modern weather prediction. His simulations show that Devonian Earth would have experienced daily temperature swings more extreme than today's. With only 11 hours of daylight, surface temperatures would have cooled more during the short nights, then heated more rapidly during the abbreviated days. The ocean circulation patterns were equally altered. Today's global ocean currents depend on a delicate balance between temperature differences, Earth's rotation, and wind patterns. Ancient Earth's rapid rotation would have driven ocean currents faster and in different directions. The Gulf Stream, which currently moderates European climate, would have been much more intense, creating a completely different global climate system. Perhaps most intriguingly, these shorter days may have influenced the evolution of life itself. Many organisms today have internal biological clocks calibrated to 24-hour cycles, circadian rhythms that regulate sleep, feeding, reproduction, and countless other biological processes. But research suggests that life may have originally evolved under much shorter day-night cycles. Dr. Carl Johnson at Vanderbilt University has studied circadian rhythms in cyanobacteria, some of the oldest life forms on Earth. Remarkably, these ancient bacteria have internal clocks that naturally run on cycles shorter than 24 hours. When isolated from external light cues, many cyanobacteria species default to rhythms between 22 and 23 hours, exactly what you might expect from organisms that evolved when days were shorter. The evidence goes deeper than just bacteria. Many plants and animals show traces of ancient timing mechanisms that don't quite match modern 24-hour days. Some flowering plants have internal rhythms that run slightly fast, requiring daily adjustment to stay synchronized with the current day-night cycle. This suggests their timing systems may be evolutionary relics from the era of shorter days. Ancient coral growth patterns provide direct evidence of how life adapted to different day lengths. Devonian corals show daily growth rings that are systematically smaller than modern coral rings, indicating they grew for shorter periods each day. But yearly growth shows they accumulated more total growth per year, suggesting they adapted to make the most of more frequent, shorter growth periods. The implications extend to animal behavior and ecology. Many modern animals are either diurnal, active during the day, or nocturnal, active at night, with activity patterns calibrated to roughly 12 hours of each condition. But on ancient Earth with 11-hour days and 11-hour nights, these patterns would have been compressed and intensified. Predator-prey relationships would have operated under completely different timing constraints. Modern migrations, seasonal behaviors, and reproductive cycles that depend on daylight duration would have functioned differently when days were shorter. Some scientists speculate that the rapid day-night cycles may have accelerated evolutionary processes by creating more frequent selection pressures. The transition from shorter to longer days wasn't uniform across Earth's surface. Due to the planet's spherical shape and axial tilt, the effects of changing rotation speed were felt differently at different latitudes. Equatorial regions experienced the most dramatic changes in day length, while polar regions saw smaller but still significant alterations to their day-night cycles. Archaeological evidence from much later periods provides hints about how humans might have adapted to different day lengths. Some ancient civilizations use timing systems that don't match modern 24-hour cycles. While these differences are small and could have many explanations, they raise intriguing questions about whether human timing systems retain any memory of ancient day lengths. Modern research into artificial lighting and shift work reveals how sensitive biological systems are to timing changes. Even small alterations to natural day-night cycles can disrupt sleep, hormone production, and metabolic processes. This sensitivity suggests that the transition from shorter to longer days may have been a significant evolutionary pressure that helped shape how life responds to environmental timing. Computer models of ancient Earth's rotation also reveal the rate of change itself. The transition from 22-hour days to 24-hour days didn't happen overnight. It took hundreds of millions of years. For any individual organism or even entire species, the change would have been imperceptible. But over evolutionary time, it represents a major environmental shift that life had to continuously adapt to. The faster rotation also affected Earth's magnetic field generation. The magnetic field depends on convection currents in Earth's molten outer core, and these currents are influenced by the planet's rotation rate. Ancient Earth's rapid rotation would have generated a stronger, more dynamic magnetic field that provided better protection against solar radiation. This enhanced magnetic protection may have been crucial for early life development. With stronger magnetic shielding, ancient Earth's atmosphere would have been better protected from solar wind erosion. This could have maintained thicker atmospheres and more stable climate conditions during critical periods in life's evolution. The study of shorter days also reveals how interconnected Earth systems really are. Day length affects rotation rate, which affects magnetic field strength, which affects atmospheric retention, which affects climate, which affects ocean circulation, which affects tidal patterns, which affects the moon's orbital evolution, which affects future day length. Every component influences every other component in an endless feedback loop. Understanding these ancient conditions helps scientists better appreciate the uniqueness of Earth's current state. But the story of shorter days raises a deeper question about Earth's future. If the moon's retreat continues slowing Earth's rotation, what will happen when days become longer than 24 hours? The same geological processes that created 22-hour days in the past are still operating today, gradually stretching our days toward 25, 26, and eventually much longer durations. This cosmic clockwork connects the ancient past to the distant future through the simple mechanism of tidal friction. Every day you experience is slightly longer than the day before, and every night, the moon hangs a little farther away in the sky. The progression from shorter days to longer days represents one of the most predictable yet profound changes happening to our planet. Chapter 5. Massive tides when the moon was closer to Earth. The ocean tides weren't just bigger. They were fundamentally different phenomena that would have made our planet nearly unrecognizable. Instead of the modest 2-meter tides we experience today, ancient Earth was subject to tidal forces so extreme they created kilometer-high walls of water that swept across entire continents twice daily. The physics behind these massive tides involves the inverse cube relationship between distance and tidal force. This means that when the moon was half its current distance from Earth, the tidal forces weren't just twice as strong. They were 8 times stronger. When the moon was at its closest approach 4.5 billion years ago, orbital mechanics calculations suggest tidal forces were over 1,000 times more powerful than anything we see today. Dr. Jacques Lasker at the Paris Observatory has calculated what these ancient tides would have looked like on a hypothetical ocean-covered Earth. His models show that 3 billion years ago, when the moon was roughly 60% of its current distance away, Oceanic tides would have reached heights of 300 meters, nearly the height of the Empire State Building. These weren't gentle waves that gradually rose and fell over hours, but catastrophic walls of water that raced across ocean basins at hundreds of kilometers per hour. But the most extreme tides occurred during Earth's earliest history, when the planet's surface was still mostly molten rock. The moon's proximity created tides not in water, but in liquid stone. These rock tides reached heights of several kilometers, creating a planetary surface that heaved and buckled like a stormy sea frozen in slow motion. Computer simulations by Dr. Robin Canop at the Southwest Research Institute reveal the staggering scale of these primordial forces. The molten Earth's surface would have deformed by 3 to 5 kilometers twice daily as the close moon passed overhead. Imagine mountain-sized bulges of liquid rock racing around Earth's surface every few hours, generating internal heat through constant deformation that may have delayed the planet's cooling and crustal formation by hundreds of millions of years. The transition from rock tides to water tides marks one of the most important moments in Earth's evolution. As the planet cooled and the moon retreated to a safer distance, Earth's surface finally solidified enough to retain stable oceans. But these early oceans experienced tidal forces still hundreds of times stronger than today's. Evidence for these massive ancient tides comes from geological formations called megaripples found in sedimentary rocks dating to over 3 billion years ago. These formations show current patterns that could only have been created by water moving at tremendous speeds and volumes. The ripple marks are orders of magnitude larger than anything produced by modern tidal currents, suggesting water velocities and volumes that dwarf contemporary tidal flows. Dr. Jody Bourgeois at the University of Washington has studied these ancient tidal deposits and found evidence of what she calls hypotidal conditions. The rock formations show signs of water depths changing by hundreds of meters within hours, creating erosion patterns and sediment deposits unlike anything seen in modern tidal environments. The biological implications of these massive tides are staggering to consider. Any early life forms would have had to survive in environments where their entire habitat could be submerged under hundreds of meters of water, then completely exposed to air twice daily. This created selection pressures unlike anything modern life has experienced. Some scientists speculate that these extreme tidal conditions may have actually accelerated the development of life by creating dynamic environments that concentrated organic molecules and provided energy for chemical reactions. Dr. David Deemer at UC Santa Cruz has proposed that tidal pools created by massive ancient tides could have served as natural laboratories for molecular evolution. The pools would have experienced repeated cycles of concentration and dilution, heating and cooling and chemical mixing that could have driven the formation of complex organic compounds. The extreme conditions would have tested molecular combinations in ways that static environments couldn't, potentially speeding up the development of self-replicating systems. As the moon gradually retreated and tidal forces weakened, life would have had to continuously adapt to changing environmental conditions. Species that thrived in the extreme tidal ranges of early Earth would have faced extinction as conditions moderated, while new species evolved to take advantage of more stable coastal environments. The retreat also changed the fundamental geography of early Earth. With tides reaching hundreds of meters high, vast areas that are now permanently dry land would have been alternately submerged and exposed twice daily. This created enormous intertidal zones where land and sea life could interact and exchange evolutionary innovations. Modern coastal environments provide only a hint of what these ancient supertidal zones would have been like. Today's largest tidal ranges, like those in the Bay of Fundy, reach about 16 meters. But ancient Earth would have had tidal zones hundreds of times larger, creating continent-sized areas of alternating marine and terrestrial conditions. The energy contained in these massive tides was beyond comprehension. Modern Earth's tides dissipate about 3.7 terawatts of energy through friction and turbulence. Ancient Earth's hypnotides would have dissipated hundreds of times more energy, generating heat equivalent to thousands of nuclear power plants running continuously. This energy dissipation had profound effects on Earth's early climate and atmospheric evolution. The constant turbulence and mixing would have enhanced the exchange of gases between the oceans and atmosphere, potentially accelerating the chemical evolution that led to oxygen-rich atmospheres and complex life. The massive tides also affected Earth's early magnetic field in ways that scientists are only beginning to understand. The rapid movement of conductive seawater through Earth's magnetic field would have generated electrical currents that could have influenced the magnetic field's strength and stability. Some researchers suggest this electromagnetic interaction may have helped maintain Earth's magnetic protection during critical periods in atmospheric evolution. Archaeological evidence of these ancient tidal conditions comes from some of the oldest rock formations on Earth. The Azua Greenstone Belt in Greenland, dating to 3.8 billion years ago, contains sedimentary structures that some geologists interpret as evidence of extreme tidal activity. The formations show current patterns and erosion features consistent with water moving at velocities far exceeding anything seen in modern environments. But perhaps the most compelling evidence comes from computer models that work backward from current conditions. When you account for the moon's observed retreat rate and run the physics in reverse, the models consistently predict tidal conditions in Earth's early history that match the geological evidence. The mathematics of orbital mechanics leaves no room for alternative explanations. The transition from massive to moderate tides wasn't gradual and uniform. During certain periods when continental configurations were favorable for tidal amplification, even the retreating moon could generate enormous tides. When continents formed barriers that focused tidal energy into narrow channels or shallow seas, local tidal ranges could temporarily reach extreme values, even as global tidal forces weakened. Dr. Mashes Green at Bangor University has modeled how changing continental positions affected tidal patterns throughout geological history. His simulations showed that even 400 million years ago, when the moon was significantly closer than today, certain coastal regions would have experienced tides over 50 meters high due to geographic amplification effects. Understanding these massive ancient tides helps explain some puzzling features of Earth's geological record. Rock formations that seem to require catastrophic flooding events may actually be evidence of normal tidal activity during periods when the moon was closer. What appears to be evidence of global catastrophes might actually be records of the everyday tidal conditions on ancient Earth. The study of ancient tides also provides insights into planetary habitability around other stars. Planets with large, close moons might experience tidal conditions similar to early Earth, potentially creating the dynamic environments needed for life to emerge. Conversely, planets without significant moons might lack the tidal energy needed to drive early biological evolution. As we look toward the future, the story of massive ancient tides reminds us that Earth's current tidal conditions are neither permanent nor necessarily optimal. But the moon's retreat raises questions about how this progression will continue. As tidal forces continue to weaken, will Earth lose some of the benefits that tidal activity provides to coastal ecosystems and global ocean circulation? The same processes that created massive ancient tides are still operating today, gradually transforming our planet toward a future with very different tidal conditions. Chapter 6. Future Consequences. The moon's relentless retreat from Earth will ultimately transform our planet into a world that bears little resemblance to the one we know today. This isn't a distant, theoretical future. It's a destiny written in the laws of orbital mechanics that will unfold with mathematical certainty over the next few billion years. Understanding this future helps us appreciate how temporary and precious Earth's current conditions really are. The most immediate consequence, already underway, is the gradual lengthening of Earth's days. Currently, each day becomes about 2.3 milliseconds longer every century, a change too small for humans to notice, but significant when accumulated over geological time. In 100 million years, Earth's days will be roughly 25 hours long. In 600 million years, a day will last about 30 hours. But this seemingly simple change cascades through every aspect of Earth's behavior in ways that compound over time. Longer days mean less efficient heat distribution between Earth's day and night sides. Currently, our 24-hour rotation cycle allows heat absorbed during the day to be partially redistributed before the next sunrise. As days lengthen, this heat distribution becomes less effective, creating more extreme temperature differences between day and night. Dr. Tyler Robinson at Northern Arizona University has modeled these future climate conditions using the same techniques astronomers use to study exoplanets. His simulations show that when Earth's days reach 48 hours, which will happen in about 2 billion years if current trends continue, the planet will experience temperature swings of 40 to 50 degrees Celsius between day and night compared to current variations of 10 to 20 degrees. These extreme temperature cycles will fundamentally alter weather patterns and ocean circulation. The atmosphere will struggle to transport heat efficiently between hemispheres, leading to more violent storms and more stagnant weather systems. Hurricanes and cyclones will become more intense but less mobile, potentially stalling over regions for weeks instead of days. Perhaps more critically, Earth's magnetic field will continue to weaken as the planet's rotation slows. The magnetic field depends on convection currents in Earth's molten outer core, driven partly by the Coriolis effect from rotation. Slower rotation means weaker Coriolis forces, which leads to less vigorous convection and a weaker magnetic field. Research published in 2019 by Dr. Julien Aubert at the University of Paris suggests that when Earth's rotation slows to about 30-hour days, the magnetic field strength will drop to roughly 50% of current levels. This weakened magnetic protection will allow more solar wind particles to reach Earth's upper atmosphere, gradually stripping away atmospheric gases over millions of years. The atmospheric loss creates a feedback loop that accelerates planetary change. As the atmosphere thins, surface pressure drops and water begins to boil at lower temperatures. This makes it harder for oceans to remain stable, potentially triggering rapid climate transitions when atmospheric pressure crosses critical thresholds. But the most dramatic future consequence involves the fate of solar eclipses. Currently, the Moon appears almost exactly the same size as the Sun when viewed from Earth, a cosmic coincidence that allows for spectacular total solar eclipses. This perfect size match is temporary and already changing. As the Moon retreats, it appears smaller in Earth's sky, while the Sun's apparent size remains constant. Total solar eclipses are gradually becoming shorter and covering smaller areas of Earth's surface. Dr. Fred Espenak, NASA's eclipse prediction expert, has calculated that the last total solar eclipse visible from Earth will occur in approximately 600 million years. After that point, the Moon will appear too small to completely cover the Sun, making only annular eclipses possible. This marks a fundamental transition in Earth's astronomical environment, the end of one of the most spectacular natural phenomena our planet has ever experienced. The loss of total eclipses represents more than just aesthetic change. Solar eclipses have historically provided crucial opportunities for astronomical discoveries, from confirming Einstein's general relativity to studying the Sun's corona. Future civilizations will lose these natural laboratories for understanding stellar physics. Even more profound changes await Earth's distant future. Computer models of long-term Earth-Moon evolution suggest that the Moon's retreat will eventually slow and reverse. This happens because the Sun's gradual brightening over time will eventually cause Earth's rotation to become tidally locked to the Moon's orbit. Dr. Klaus Measure at the University of Bern has calculated that in roughly 50 billion years, Earth and the Moon will reach a state called double tidal locking. At this point, Earth will always show the same face to the Moon, just as the Moon currently shows only one face to Earth. A day and a month will both last about 47 current days. This double-locked configuration represents the final stable state of the Earth-Moon system, assuming both bodies survive the Sun's eventual expansion into a red giant star. The Moon will have retreated to about 1.6 times its current distance, appearing roughly 40% smaller than today's Moon. Tides will be much weaker, and Earth climate will be dominated by the extreme day-night cycle. The journey toward double tidal locking isn't smooth and gradual. Orbital dynamics calculations suggest the system will go through several transitional phases with different characteristics. During some periods, the Moon's orbit may become slightly elliptical, creating variable tidal forces that alternate between stronger and weaker influences. These orbital variations could trigger climate instabilities unlike anything in Earth's past. When the Moon is at its closest approach during an elliptical phase, tidal forces would strengthen temporarily, potentially destabilizing ice sheets or altering ocean circulation patterns. When the Moon reaches its farthest point, the sudden reduction in tidal influence could trigger different climate responses. The biological implications of these future changes are staggering to contemplate. Life on Earth has evolved for billions of years under gradually changing, but relatively stable day lengths. The transition to 30-hour, 40-hour, or eventually 47-day cycles will challenge fundamental biological processes that have been conserved since life began. Many organisms might adapt by changing their internal timing mechanisms, but others could face extinction if they can't adjust to the new environmental rhythms. Entire ecosystems that depend on current day-night cycles for migration, reproduction, and feeding could collapse as these cycles become too long to sustain traditional biological patterns. Plant photosynthesis will face particular challenges. Many plants have evolved to optimize their energy production for current daylight durations. Extremely long days might initially seem beneficial for photosynthesis, but the corresponding long nights could create problems with energy storage and cellular maintenance that outweigh any advantages. The weakening magnetic field adds another layer of biological pressure. Increased radiation exposure from solar particles could force surface life to develop better radiation protection or retreat to underground environments. This could drive evolution in directions that favor radiation resistance over other adaptive traits. Ocean ecosystems will face their own challenges as tidal mixing decreases and temperature stratification increases. Many marine food chains depend on tidal currents and mixing to distribute nutrients and maintain water quality. Weaker tides could lead to more stagnant ocean conditions and the expansion of oxygen-poor zones. Perhaps most remarkably, these future changes are essentially guaranteed by the laws of physics. Unlike climate change or asteroid impacts, which involve complex systems with many variables, the Moon's retreat follows predictable gravitational dynamics. Barring some catastrophic intervention, Earth will definitely experience these transformations over the next few billion years. Understanding this certain future helps put current environmental challenges in perspective. The Earth we're working to preserve today represents a brief, stable phase in our planet's evolution, a phase that will eventually end regardless of human actions. This doesn't diminish the importance of environmental protection, but it adds a cosmic context to our stewardship of Earth's current conditions. The Moon's retreat also raises questions about the long-term habitability of planets around other stars. How many worlds maintain stable, life-friendly conditions for billions of years? And how many experience dramatic transitions like Earth's future? The specific orbital mechanics that allowed Earth to have both massive ancient tides and moderate current tides may be much rarer in the universe than previously thought. Chapter 7. Magnetic Weakening, hidden beneath your feet. Earth's molten iron core is generating an invisible shield that protects all life from deadly solar radiation. This magnetic field extends tens of thousands of kilometers into space, deflecting charged particles that would otherwise strip away our atmosphere and sterilize the planet's surface. But as the moon retreats and Earth's rotation gradually slows, this crucial protective barrier is slowly weakening, a process that will fundamentally alter our planet's habitability over the next billion years. The connection between Earth's rotation and its magnetic field operates through a process called the geodynamo effect. Deep inside Earth, the outer core consists of liquid iron and nickel flowing around the solid inner core. Earth's rotation creates Coriolis forces that organize these flows into helical patterns, generating electrical currents that produce the magnetic field. Faster rotation creates stronger Coriolis forces, which drive more vigorous convection and generate a more powerful magnetic field. Dr. Christopher Davies at the University of Leeds has used supercomputer simulations to model how changing rotation rates affect the geodynamo. His research shows that magnetic field strength is directly proportional to rotation rate raised to the power of 0.5, meaning that when rotation slows down, magnetic field strength decreases, but not linearly. A 10% decrease in rotation rate results in about a 5% decrease in magnetic field strength. This relationship has profound implications for Earth's future. As the moon's retreat continues slowing Earth's rotation, the magnetic field will steadily weaken over hundreds of millions of years. Current measurements show Earth's rotation slowing by about 2.3 milliseconds per century, which translates to a magnetic field weakening of roughly 1.2 parts per million annually. While this rate might seem negligible, the effects accumulate over geological time. In 100 million years, when Earth's days are about 25 hours long, the magnetic field will be approximately 96% of its current strength. In 500 million years, with 28-hour days, the field strength will drop to about 91% of today's levels. By the time Earth reaches the double-locked state with 47-day cycles, the magnetic field could be less than 80% of its current intensity. But these calculations assume Earth's core composition and dynamics remain constant, which may not be realistic. Dr. Julien Aubert at the Institut de Physique du Globe in Paris has discovered that the geodynamo system has multiple stable states, and slow rotation changes could potentially trigger transitions between these states, causing more dramatic magnetic field variations. Historical evidence suggests Earth's magnetic field has already experienced significant changes correlated with rotation rate variations. Paleomagnetic studies of ancient rocks reveal periods when the magnetic field was much stronger or weaker than today, sometimes lasting millions of years. Some of these variations coincide with geological evidence for changes in Earth's rotation rate caused by major continental rearrangements. The most dramatic example occurred during the late Archean period, about 2.5 billion years ago, when Earth's rotation was significantly faster, but the magnetic field appears to have been weaker than expected. This paradox might be explained by differences in core dynamics when Earth was hotter and the inner core was smaller or non-existent. Dr. Peter Driscoll at the Carnegie Institution for Science has proposed that Earth's magnetic field evolution is more complex than simple rotation dependence models suggest. His research indicates that the growth of the inner core over geological time has been a major factor in magnetic field strength, potentially compensating for rotational slowing until the inner core reaches its maximum size. However, this compensation effect is temporary. The inner core is gradually approaching its maximum possible size as Earth's interior continues cooling. Once inner core growth stops, probably within the next billion years, rotational slowing will become the dominant factor controlling magnetic field strength. The weakening magnetic field will have cascading effects on Earth's atmosphere and climate. Currently, the magnetosphere deflects most of the solar wind. A stream of charged particles flowing from the sun at speeds of 300 to 800 kilometers per second. Without adequate magnetic protection, these particles can directly interact with atmospheric molecules, gradually stripping them away through a process called atmospheric escape. Mars provides a cautionary example of what happens to planetary atmospheres without strong magnetic protection. Mars once had a substantial atmosphere and possibly liquid water on its surface, but its weak magnetic field allowed solar wind erosion to strip away most of its atmospheric mass over billions of years. While Earth's stronger gravity gives it better atmospheric retention than Mars, the same fundamental process operates on our planet. Research by Dr. Gina DiBraccio at NASA's Goddard Space Flight Center has measured current atmospheric escape rates from Earth using data from the THEMIS satellite mission. Her team found that Earth currently loses about 90 tons of atmospheric material per day through magnetic field interactions with the solar wind. As the magnetic field weakens, this loss rate will gradually increase. The atmospheric escape process preferentially removes the lighter elements like hydrogen and helium while leaving heavier molecules behind. Over extremely long timescales, this could alter the composition of Earth's atmosphere in ways that affect climate stability and the greenhouse effect. Water vapor loss represents a particularly serious long-term concern. Solar ultraviolet radiation can break apart water molecules in the upper atmosphere, releasing hydrogen that can escape to space if magnetic protection is inadequate. Venus likely experienced runaway water loss through this mechanism early in its history, contributing to its current hellish conditions. Dr. Feng Tien at Tsinghua University has modeled how weakening magnetic fields might affect Earth as water retention over geological time. His calculations suggest that magnetic field strength below 50% of current levels could trigger accelerated water loss, particularly if combined with increasing solar luminosity as the sun ages. The biological implications of magnetic field weakening extend beyond atmospheric protection. Many species use Earth's magnetic field for navigation during migration, including birds, sea turtles, and some marine mammals. As field strength decreases and field lines become less organized, these navigation systems could become less reliable. Some research suggests that magnetic field variations might also affect human health and behavior. Studies have found correlations between geomagnetic activity and various biological processes, though the mechanisms remain poorly understood. A permanently weakened magnetic field might have subtle but widespread effects on biological systems that evolved under current field conditions. The most immediate effects of magnetic field weakening will be felt in Earth's upper atmosphere and space environment. Satellites and spacecraft already experience increased radiation exposure during geomagnetic storms when the magnetic field temporarily weakens. A permanently weakened field would create a more hostile space environment around Earth, requiring better radiation shielding for both human space activities and electronic systems. GPS satellites, which orbit above much of Earth's magnetic protection, would be particularly vulnerable to increased radiation from solar particles. Communication satellites in geostationary orbit, already exposed to significant radiation, might require more frequent replacement or heavier shielding as magnetic protection decreases. The International Space Station and other low Earth orbit facilities would experience increased radiation exposure, particularly during solar storms. Astronauts might need to limit their time in space or use better radiation shielding to maintain current safety standards. Ground-based technology could also be affected as weakened magnetic fields allow more solar particles to reach lower altitudes. Power grids at high latitudes already experience disruptions during strong geomagnetic storms, and these effects could become more frequent and extend to lower latitudes as magnetic protection decreases. The aurora phenomena, the northern and southern lights, will also change as magnetic field configurations evolve. Aurora occur when solar particles interact with atmospheric gases along magnetic field lines. Weakened fields might create different aurora patterns, possibly making them visible at lower latitudes while reducing their intensity at polar regions. Despite these concerning implications, Earth's magnetic field will likely remain strong enough to prevent catastrophic atmospheric loss for billions of years. The field would need to weaken to less than 10% of current strength before atmospheric escape rates approach those of Mars. And rotation-induced weakening alone is unlikely to reduce field strength by that much. However, the combination of rotational slowing, inner core evolution, and solar luminosity increases could create a more complex scenario. Dr. Rory Barnes at the University of Washington has developed models suggesting that Earth's magnetic field could experience periodic collapses and recoveries as the core dynamics respond to changing rotation rates and thermal evolution. Understanding magnetic field weakening helps put Earth's long-term habitability in perspective. The magnetic shield that currently protects life is not permanent or unchanging. It is part of a dynamic system that has been evolving throughout Earth's history and will continue evolving as long as the planet exists. The Moon's retreat represents just one factor affecting this evolution, but it's a factor that operates with predictable consistency over geological time. As our satellite continues its slow journey away from Earth, it's gradually reducing one of the fundamental forces that helps maintain our planet's habitability. Chapter 8. Other moons. Earth's moon is not alone in its retreat from its parent planet. Throughout our solar system, gravitational choreography is constantly reshaping the relationships between planets and their satellites in ways that provide crucial insights into the ultimate fate of the Earth-Moon system. Some moons are spiraling outward, like our own, while others are doomed to spiral inward toward destruction, creating a cosmic laboratory for understanding tidal evolution. The physics governing these orbital migrations follows the same fundamental principles that drive our moon's retreat, but the outcomes vary dramatically depending on specific conditions. The key factor is whether the moon orbits faster or slower than its planet rotates. When a moon orbits faster than its planet spins, tidal forces cause the moon to spiral inward toward eventual destruction. When a moon orbits slower than its planet spins, like our moon, tidal forces push it outward to greater distances. Mars provides the most dramatic example of inward spiral in our solar system. Its tiny moon Phobos, only 22 kilometers across, orbits Mars once every 7.6 hours, while Mars rotates once every 24.6 hours. This means Phobos orbits faster than Mars spins, creating tidal forces that are steadily dragging it closer to the planet's surface. Dr. Benjamin Black at the City College of New York has calculated that Phobos is spiraling inward at a rate of about 1.8 centimeters per year, roughly half the rate at which our moon moves away from Earth, but in the opposite direction. In approximately 50 million years, Phobos will cross Mars' Roche limit and be torn apart by tidal forces, creating a spectacular ring system around the red planet. The destruction of Phobos won't happen gradually. Computer simulations by Dr. Tushar Mittal at MIT show that when Phobos reaches the critical distance, tidal forces will overwhelm the moon's weak gravitational self-attraction within a matter of decades. The moon will literally be stretched apart like taffy, creating a debris ring that will persist for millions of years before the particles either fall to Mars' surface or escape to space. This process isn't theoretical. We can observe it happening. High-resolution images from NASA's Mars Reconnaissance Orbiter show linear grooves across Phobos' surface that appear to be stress fractures caused by increasing tidal forces. These grooves are widening measurably as the moon gets closer to Mars, providing real-time evidence of tidal destruction in progress. Jupiter's system offers an even more complex example of tidal evolution involving multiple moons. The four large Galilean moons, Io, Europa, Ganymede, and Callisto, are locked in an intricate gravitational dance that demonstrates how tidal forces can create both inward and outward migration simultaneously. Io, the innermost large moon, experiences the most extreme tidal forces in the solar system. Jupiter's gravity stretches and compresses Io by up to 100 meters twice during each orbit, generating enough internal heat to power over 400 active volcanoes. This tidal heating makes Io the most geologically active body in the solar system, with surface features that change visibly over periods of months. Dr. Krishan Khurana at UCLA has used magnetic field measurements from NASA's Galileo spacecraft to study how Jupiter's moons are migrating. His research reveals that Io is slowly spiraling inward while Europa and Ganymede are moving outward, creating a complex system where gravitational resonances between the moons affect their individual evolution rates. The Europa-Ganymede system is particularly fascinating because these moons are locked in a 2-to-1 orbital resonance. Europa completes exactly 2 orbits for every 1 orbit of Ganymede. This resonance was created by tidal evolution in the past and continues to influence how both moons migrate today. As Europa moves outward, it maintains this precise resonance with Ganymede, demonstrating how tidal forces can create stable, long-term orbital arrangements. Saturn's moon system provides perhaps the most spectacular example of tidal evolution currently observable. The planet's iconic rings are likely the remnants of moons that were destroyed by tidal forces millions of years ago. But Saturn still retains over 80 moons, many of which are actively migrating due to tidal interactions. Titan, Saturn's largest moon, is moving away from Saturn at approximately 11 centimeters per year, nearly 3 times faster than our moon's retreat from Earth. Dr. Paolo Tortora at the University of Bologna has measured this migration using precise radio tracking of the Cassini spacecraft during its 13-year mission at Saturn. The rapid migration of Titan reveals something surprising about Saturn's interior structure. For Titan to retreat so quickly, Saturn must dissipate tidal energy much more efficiently than previously thought. This suggests that Saturn's interior is more fluid and responsive to tidal deformation than standard models predicted, possibly indicating a partially molten core or unusually deep atmospheric layers. Enceladus, another of Saturn's moons, demonstrates how tidal forces can create conditions for potential life. This ice-covered moon is locked in a 2-to-1 resonance with the moon Dione, creating orbital eccentricity that generates tidal heating. The internal heat melts ice beneath Enceladus' surface, creating a subsurface ocean that erupts through geysers at the South Pole. The Cassini mission detected organic molecules and other potential biosignatures in these geyser plumes, making Enceladus one of the most promising places to search for extraterrestrial life. The tidal heating that makes this possible is the same process that drives our moon's retreat from Earth, demonstrating how tidal evolution can create habitable environments throughout the solar system. Pluto's system provides an example of what happens when tidal evolution reaches completion. Pluto and its largest moon, Charon, are mutually tidally locked. They always show the same faces to each other, rotating and orbiting with identical periods of 6.4 days. This represents the final state that Earth and Moon are slowly approaching over billions of years. Dr. Douglas Hamilton at the University of Maryland has studied the Pluto-Charon system as a preview of Earth's far future. In this double-locked configuration, there are no longer any tidal forces between the two bodies, so orbital migration stops completely. Charon orbits at a stable distance that never changes, providing a glimpse of the ultimate fate of the Earth-Moon system. The study of other planetary systems reveals that tidal evolution is a universal process affecting every moon in the solar system. Dr. Francis Nimmo at UC Santa Cruz has cataloged migration rates for dozens of moons and found that virtually every satellite is either moving inward or outward due to tidal forces. Some of the most extreme examples occur around the outer planets, where large moons orbit rapidly rotating planets. Neptune's moon Triton is spiraling inward so rapidly that it will be destroyed by tidal forces in approximately 100 million years. Triton's retrograde orbit, it orbits backward relative to Neptune's rotation, creates particularly strong tidal dissipation that accelerates its doom. These observations help scientists understand what factors determine whether tidal evolution leads to moon escape or moon destruction. Planets that rotate rapidly tend to push their moons outward, while planets with slow rotation tend to capture their moons in death spirals. The size and composition of both the planet and moon also play crucial roles in determining migration rates and ultimate fates. Recent discoveries of exoplanet systems with close orbiting moons provide additional perspectives on tidal evolution. The Kepler Space Telescope has identified several planetary systems where large moons appear to be spiraling into their host planets, creating detectable signatures as they block starlight during transit events. Dr. David Kipping at Columbia University leads the Hunt for Exomoons project, which uses these transit signatures to study moon evolution around distant stars. His research suggests that many large moons are destroyed by tidal forces during planetary system evolution, which might explain why large moons like our own are relatively rare in the universe. The comparative study of moon evolution also reveals how unique Earth's situation really is. Our moon formed at just the right distance to avoid immediate tidal destruction, but far enough away to eventually retreat to safety. Most moons that form close to their planets get destroyed quickly, while moons that form far away may never experience the strong tidal forces needed to drive early planetary evolution. Understanding how other moons behave under tidal forces helps scientists refine models of Earth's future evolution. By observing systems like Saturn's rapidly migrating Titan or Jupiter's tidally heated Io, researchers can test theories about how tidal energy dissipation works under different conditions. The diversity of outcomes in other planetary systems also highlights how special Earth's current phase of evolution really is. We happen to live during a period when our moon is at an optimal distance, close enough to create significant tides that benefit Earth's climate and biology, but far enough away to be stable for billions of years. This cosmic perspective reveals that the moon's retreat isn't an isolated phenomenon, but part of a universal process that shapes planetary systems throughout the universe. Every moon tells a story about gravitational forces operating across deep time, and Earth's moon is just one chapter in this ongoing cosmic narrative. Chapter 9. Deep Time. To truly comprehend the moon's retreat from Earth, you must expand your perception of time beyond anything human minds naturally grasp. The 3.8 centimeters per year that our satellite moves away from us becomes meaningful only when viewed across the vast expanses of geological time, eons so long that entire mountain ranges rise and erode to dust. Continents drift across the globe, and evolution transforms life from single cells into the complex biosphere we see today. Consider this. In the time it takes for the moon to retreat just 1 kilometer from Earth, roughly 26,000 years, human civilization has evolved from scattered hunter-gatherer bands to a global technological society. The pyramids of Egypt, among our oldest monumental architecture, were built when the moon was only 7 centimeters closer than today. The entire recorded history of human civilization represents less than 20 centimeters of lunar retreat. Yet the moon has been moving away from Earth for 4.5 billion years, accumulating a total migration distance of over 340,000 kilometers from its original position, just 22,000 kilometers above Earth's surface. To put this in perspective, the moon has traveled roughly 15 times farther during its retreat than the distance around Earth's equator. This migration represents one of the longest duration phenomena that science can observe and measure. Dr. Stephen Moses at the University of Colorado studies some of Earth's oldest rocks to understand how the Earth-Moon system has evolved across deep time. His research reveals that the moon's retreat has been the most consistent astronomical process affecting Earth throughout the planet's entire history. While asteroid impacts, volcanic eruptions, and climate changes operate on shorter timescales measured in thousands or millions of years, the moon's migration has continued uninterrupted for billions of years. The consistency of this process across deep time becomes remarkable when you consider all the events that have occurred during the moon's journey. The moon began its retreat when Earth's surface was mostly molten rock. It continued moving away as the first oceans formed, as life emerged in those oceans, as oxygen began accumulating in the atmosphere, and as complex cells evolved. The moon kept retreating during every mass extinction event, every ice age, and every major geological transformation that Earth has experienced. This temporal perspective reveals that the moon's retreat operates on what scientists call astronomical time, scales so vast that they dwarf human experience and even most geological processes. While mountains take millions of years to form and continents take tens of millions of years to drift significant distances, the moon's migration unfolds over thousands of millions of years. Dr. Bradley Jove at Washington University has studied lunar samples returned by Apollo missions to understand how the moon itself has changed during this long journey. The rocks reveal that early in its retreat, the moon was still hot from its formation and experienced global volcanism that lasted for over 1 billion years. Ancient lunar lava flows, visible today as dark patches on the moon's surface, were created while the moon was much closer to Earth and experiencing different tidal stresses. The retreat rate itself has varied dramatically across deep time, providing a window into Earth's changing interior dynamics and surface conditions. During the first billion years after formation, the moon retreated much more rapidly because Earth's molten surface allowed extremely efficient tidal energy dissipation. As Earth cooled and developed a solid crust, the retreat rate slowed to more gradual levels. But the story becomes more complex when you account for changing continental configurations. Dr. Mashes Green at Bangor University has reconstructed how tidal patterns evolved as continents drifted across Earth's surface over the past 540 million years. His models show that the moon's retreat rate has fluctuated by factors of 2 or 3, depending on how continental masses were arranged to focus or dissipate tidal energy. During the breakup of the supercontinent Pangaea between 300 and 200 million years ago, new ocean basins formed that dramatically increased global tidal friction. The moon's retreat rate during this period may have been 50 to 100% faster than today's rate. Conversely, when continents were arranged to minimize tidal dissipation, the retreat rate slowed significantly below current levels. These variations mean that the moon's migration hasn't been perfectly uniform across deep time. Instead, it has proceeded in phases characterized by different retreat rates depending on Earth's changing surface conditions. The current retreat rate of 3.8 centimeters per year represents just one moment in a 4.5 billion year story of changing orbital dynamics. The deep time perspective also reveals how the moon's retreat connects to the largest scale processes affecting Earth. The gradual slowing of Earth's rotation due to tidal friction has influenced everything from the strength of the magnetic field to the dynamics of plate tectonics. Some researchers speculate that changing rotation rates may have affected the timing of major evolutionary transitions by altering climate patterns and environmental stability. Dr. Ross Mitchell at the Chinese Academy of Sciences has proposed that the moon's retreat may be connected to cycles of supercontinent formation and breakup that occur roughly every 400 to 500 million years. As continents come together and split apart, they change global tidal patterns in ways that could influence the moon's migration rate and Earth's rotational evolution. The concept of deep time also helps explain why the moon's retreat was invisible to human observers until recently. Even with careful astronomical observations spanning thousands of years, the The cumulative effect would be too small to detect without modern precision measurement techniques. Ancient astronomers, who recorded eclipses and planetary positions with remarkable accuracy, had no way to perceive the moon's gradual recession because it occurs on timescales far beyond human perception. This invisibility to direct human observation makes the moon's retreat one of the most counterintuitive major processes affecting Earth, unlike earthquakes, volcanic eruptions, or even continental drift, which can be observed directly over human lifetimes. The moon's migration requires sophisticated instruments and decades of measurements to detect and confirm. The laser ranging experiments that measure the moon's retreat began only in 1969, giving us just over 50 years of direct observations. While this represents an impressive achievement in precision measurement, it's equivalent to observing just 0.00001% of the moon's total migration time. Imagine trying to understand the growth of a forest by watching it for 1 second out of an entire century. Yet this tiny observational window has revolutionized our understanding of how planetary systems evolve. By measuring the moon's current retreat rate and combining it with theoretical models of tidal evolution, scientists can reconstruct the entire 4.5 billion year history of the Earth-Moon system with remarkable confidence. The deep time perspective also provides context for understanding humanity's place in this cosmic story. Modern humans have existed for roughly 200,000 years, about 0.004% of the time the moon has been retreating. Our entire species has witnessed only 8 meters of lunar recession, a distance you could walk in a few seconds. Yet we live during a particularly interesting phase of this retreat, when the moon appears almost exactly the same size as the sun and creates the spectacular total solar eclipses that have inspired human wonder throughout history. Dr. Anthony Dobrovolskis at UC Irvine has calculated that the golden age of perfect solar eclipses, when the moon's apparent size closely matches the sun's, represents only about 5% of the moon's total retreat timeline. Before this period, the moon was too large and created overly dramatic eclipses. After this period, which will end in roughly 600 million years, the moon will be too small to create total eclipses at all. This temporal context reveals that humans are witnessing Earth during a remarkable but temporary phase of its evolution. The moderate tides, 24-hour days, and perfect solar eclipses that define our current Earth are just one moment in a 4.5 billion year progression of changing conditions. The deep time view also extends into Earth's far future, where the moon's retreat will eventually slow and reverse as the sun's gradual brightening affects Earth's rotational dynamics. The ultimate double-locked state, where Earth and moon always show the same faces to each other, lies roughly 50 billion years in the future, a timeline so vast it's 250 times longer than the age of complex life on Earth. Understanding deep time transforms how you think about permanence and change. The moon that appears fixed and eternal in our sky is actually engaged in a journey that began before life existed on Earth and will continue long after the sun becomes a red giant star. Every night you look up at the moon, you're witnessing one tiny moment in the longest astronomical process that directly affects our planet. This perspective connects the moon's retreat to the most fundamental questions about cosmic evolution and the nature of time itself. The same gravitational forces that drive lunar migration operate throughout the universe, reshaping planetary systems around distant stars across timescales that span the entire history of the cosmos. Chapter 10: Cosmic Significance. The moon's retreat from Earth represents far more than a local astronomical curiosity. It embodies fundamental principles of cosmic evolution that operate throughout the universe. This seemingly simple process connects Earth's history to the largest questions in astrophysics. How do planetary systems evolve? What makes worlds habitable? And how does the universe itself change across deep time? When you understand that tidal evolution affects every planetary system in the cosmos, The moon's migration becomes a window into universal processes that have been reshaping worlds since the first stars formed. Around every star with planets, gravitational forces are constantly adjusting orbital relationships, transferring energy between rotation and revolution, and determining the ultimate fates of countless worlds. Dr. Rory Barnes at the University of Washington has studied how tidal evolution affects planetary habitability around other stars. His research reveals that the Earth-Moon system's particular characteristics, a large satellite formed by giant impact, orbiting at just the right distance to avoid destruction while providing beneficial tidal forces, may be much rarer in the universe than previously thought. Most planetary systems don't have moons like ours. The majority of exoplanets discovered by the Kepler Space Telescope orbit much closer to their stars than Earth orbits the Sun, creating different tidal environments where stellar tides dominate over any moon-planet interactions. In these systems, the star itself acts like Earth's moon, raising tides on the planet and potentially locking it into eternal day and night sides. The absence of large moons around most exoplanets suggests that the giant impact event that created our moon was an extraordinary occurrence. Dr. Robin Canup at the Southwest Research Institute estimates that only 1 to 10% of Earth-sized planets experience the specific collision conditions needed to form a large satellite. This rarity makes the Earth-Moon system's tidal evolution a unique cosmic experiment that provides insights into processes that may be uncommon in the universe. But the principles governing our moon's retreat operate universally. Every gravitational interaction between rotating bodies involves energy transfer, angular momentum conservation, and the gradual evolution toward tidal equilibrium. These same physics control the evolution of binary star systems, the migration of exoplanets, and even the dynamics of galaxies containing billions of stars. Binary star systems provide spectacular examples of tidal evolution on cosmic scales. When two stars orbit close to each other, tidal forces can transfer mass between them, alter their rotation rates, and eventually cause them to merge in explosive events. The gravitational wave detectors LIGO and Virgo have observed dozens of such mergers, revealing how tidal evolution drives some of the most energetic phenomena in the universe. Dr. Vasiliki Kalajera at Northwestern University studies how tidal forces in binary star systems can accelerate stellar evolution and create exotic objects, like neutron stars and black holes. Her research shows that tidal energy transfer can force stars to rotate synchronously with their orbits, just as Earth and Moon are slowly approaching a similar locked configuration. The Moon's retreat also connects to fundamental questions about time and cosmic evolution. The gradual slowing of Earth's rotation represents a net decrease in rotational energy throughout the Earth-Moon system. This energy loss is eventually radiated away as heat, contributing to the overall increase in entropy that drives cosmic evolution. Dr. Sean Carroll at Caltech has explored how local processes like tidal evolution connect to the arrow of time that governs the entire universe. The Moon's retreat represents a concrete example of how gravitational systems naturally evolve from more organized states, Earth spinning rapidly with a close moon, toward less organized states, Earth spinning slowly with a distant moon. This connection to thermodynamics and the nature of time reveals that the Moon's migration isn't just an astronomical phenomenon. It's part of the fundamental tendency for energy to dissipate and systems to reach equilibrium that drives all cosmic evolution. From the cooling of the universe after the Big Bang to the formation of stars and galaxies, the same principles that govern tidal evolution operate on every scale in nature. The study of tidal evolution also provides insights into the search for life beyond Earth. Dr. Renee Heller at the Max Planck Institute has calculated that planets with large moons like Earth's may be more likely to develop and maintain stable climates suitable for complex life. The Moon's gravitational influence helps stabilize Earth's axial tilt, preventing chaotic climate variations that might disrupt biological evolution. But the Moon's retreat suggests this stabilizing influence is temporary. As our satellite moves farther away, its ability to stabilize Earth's rotation axis will gradually weaken. In billion-year timescales, Earth may begin experiencing larger variations in axial tilt that could destabilize climate patterns and challenge the long-term survival of complex life. This temporal limitation on lunar stabilization may explain why complex life took so long to evolve on Earth. Perhaps the first few billion years of Earth's history, when the Moon was closer but tidal forces were more extreme, were unsuitable for complex organisms. Only when the Moon retreated to an optimal distance, neither too close nor too far, could stable conditions emerge that allowed complex life to flourish. The Moon's current distance may represent a Goldilocks zone for lunar influences, close enough to provide beneficial tides and axial stabilization, but far enough away to avoid the extreme conditions of early Earth. This optimal zone is moving farther from Earth as the Moon continues its retreat, suggesting that Earth's current habitability represents a temporary phase in planetary evolution. Understanding this temporal aspect of habitability has profound implications for astrobiology and the search for extraterrestrial intelligence. If complex life requires not just the right planetary conditions, but also the right timing in a planet's tidal evolution, then intelligent life may be much rarer in the universe than estimates based solely on planetary characteristics suggest. Dr. Aditya Chopra at the Australian National University has proposed that the Great Filter, the hypothetical evolutionary bottleneck that might explain why we haven't detected other technological civilizations, could be related to tidal evolution and the narrow windows of time when planets maintain optimal conditions for complex life. The Moon's retreat also provides a cosmic perspective on human technological development. The laser-ranging experiments that measure lunar recession represent one of the most precise measurements in all of science, accurate to within a few centimeters across nearly 400,000 kilometers. This achievement demonstrates humanity's growing ability to perceive and understand cosmic processes operating on timescales far beyond direct human experience. Future space missions may extend these measurements to other planetary systems. Proposed interferometric telescopes could potentially detect tidal evolution around nearby stars by measuring tiny changes in planetary orbital periods over decades of observation. Such measurements would provide direct evidence of how common Earth-like tidal processes are throughout the galaxy. The Moon's retreat also connects to questions about the far future of cosmic evolution. As the universe continues expanding and cooling, stellar formation will eventually cease, leaving only long-lived red dwarf stars that could shine for trillions of years. Planetary systems around these stars will experience extremely long-term tidal evolution that could fundamentally alter their characteristics over cosmic time. Dr. Fred Adams at the University of Michigan has modeled how planetary systems will evolve in the far future when the universe is dominated by red dwarf stars. His calculations suggest that tidal forces will gradually synchronize most planets with their orbital periods, creating worlds with permanent day and night sides. The Moon's current retreat from Earth provides a preview of similar processes that will affect countless worlds across deep time. Perhaps most profoundly, the Moon's migration reminds us that nothing in the universe is truly permanent or unchanging. The seemingly eternal celestial dance between Earth and Moon is actually a temporary phase in an ongoing evolution that has been proceeding for billions of years and will continue for billions more. This perspective challenges human intuitions about stability and permanence. The Moon that has inspired art, literature, religion, and science throughout human history is gradually abandoning us, following the inexorable laws of physics toward a future when Earth will be a very different world. Yet this same cosmic perspective also reveals the remarkable privilege of witnessing the universe during this particular epoch. We live during the brief period when Earth has moderate tides, 24-hour days, and perfect solar eclipses. We exist at a moment when complex life can thrive in the optimal zone of lunar influence. We have developed the technology to measure and understand cosmic processes operating across deep time. The moon's retreat from Earth thus becomes a meditation on time, change, and our place in the cosmic story. It connects the intimate human experience of looking up at the moon to the vast scales of space and time that govern the evolution of the universe itself. In understanding why the moon is moving away from Earth, we gain insight into fundamental processes that shape every world, every star, and every galaxy across the entire cosmos. Throughout this journey, we've discovered that the moon's retreat from Earth is simultaneously one of the most predictable and most transformative processes affecting our planet. We've seen how tidal forces transfer energy from Earth's rotation to the moon's orbit, driving a migration that has continued for 4.5 billion years. We've explored geological evidence preserved in ancient corals and rock formations that proves days were shorter and the moon was closer throughout Earth's history. And we've glimpsed a future where Earth spins so slowly that days and weeks, total solar eclipses become impossible, and our planet's magnetic field weakens to dangerous levels. But perhaps the most profound insight is how this gradual cosmic separation connects every aspect of Earth's evolution. The moon's retreat has influenced the development of life, the stability of climate, the strength of our magnetic field, and even the fundamental nature of time itself in our world. Every sunrise happens slightly later than it would if the moon stood still. Every tide that rises and falls participates in this ancient gravitational conversation between Earth and its satellite. The retreat also reveals something beautiful about the nature of cosmic time. While human civilizations rise and fall over thousands of years, and species evolve and go extinct over millions of years, the moon's migration unfolds over billions of years, a timeline so vast it encompasses the entire history of complex life on Earth. Yet, this seemingly eternal process operates through forces so subtle they were invisible to human observation, until the space age gave us the precision instruments needed to measure centimeter-scale changes across hundreds of thousands of kilometers. We've seen how other moons throughout the solar system are engaged in their own gravitational dances, some spiraling inward toward destruction, while others migrate outward toward freedom. Mars' doomed moon Phobos reminds us that not every satellite escapes the tidal forces that created it. Jupiter's volcanic moon Io shows us what happens when tidal forces become extreme. Saturn's retreating moon Titan hints at the complex internal dynamics that govern planetary evolution. The geological evidence locked in Earth's ancient rocks tells a story of constant change operating beneath the appearance of stability. Devonian corals recorded 400-day years when our planet spun faster and the moon loomed larger in the sky. Precambrian rock formations preserve evidence of massive tides that would have made Earth nearly unrecognizable to modern observers. These archives prove that the moon's retreat isn't a modern discovery, but a fundamental process that has shaped Earth since our satellite formed. Understanding the moon's migration also provides perspective on humanity's place in cosmic history. We happen to live during a remarkable but temporary phase when the moon appears almost exactly the same size as the sun, creating the perfect solar eclipses that have inspired wonder throughout human history. This cosmic coincidence is already ending as the moon retreats in 600 million years. Total solar eclipses will become impossible as the moon appears too small to cover the sun completely. The weakening of Earth's magnetic field as rotation slows adds another layer of complexity to our planet's far future. The invisible shield that currently protects life from solar radiation will gradually diminish as the moon's retreat robs Earth of rotational energy. While this process unfolds over timescales far beyond human concern, it demonstrates how intimately connected seemingly separate planetary systems really are. As you go about your daily life after watching this, Remember that you're experiencing a brief moment in a 4.5 billion year cosmic story that's still being written. When you see the moon rising over the horizon, consider that it's slightly farther away than it was last month, last year, and certainly farther than when the first humans looked up and wondered about that bright disk in the night sky. The moon that inspired the earliest myths and legends was measurably closer to Earth than the one you see today. When you feel ocean tides or notice the changing phases, remember that these phenomena are gradually weakening as the moon retreats. The same tidal forces that create peaceful waves on beaches are participating in a cosmic energy transfer that has been reshaping our planet longer than life has existed in Earth's oceans. The moon's retreat connects us to the deepest principles governing how the universe works. Energy conservation, angular momentum transfer, and gravitational dynamics operate the same way around distant stars as they do in our own Earth-Moon system. By understanding why our moon is leaving us, we gain insight into processes that affect every planetary system in the cosmos. Perhaps most remarkably, this story continues every moment. As you sleep tonight, the moon will be slightly farther away when you wake up tomorrow morning. The process that began when Earth was a molten ball orbited by a massive, close satellite continues today with the same relentless consistency that has characterized it for billions of years. You are not separate from this cosmic dance. You are part of it. Every step you take is affected by gravitational forces that also drive the moon's retreat. Every day you experience is slightly longer than the days experienced by your ancestors because of energy transferred from Earth's rotation to the moon's orbit. You exist during a unique epoch in Earth's history when tidal forces are moderate enough to permit complex life, but strong enough to drive continued planetary evolution. The moon's departure reminds us that nothing in the universe is truly permanent, but it also reveals the magnificent predictability of physical laws operating across deep time. The same forces that have guided the moon's 4.5 billion year journey from close proximity to its current distance will continue operating for billions of years into the future, eventually creating an Earth that rotates slowly under a small, distant moon in a cosmic ballet that reaches perfect synchronization. If you found this exploration of cosmic time and gravitational evolution fascinating, give this video a thumbs up and subscribe for more journeys into the deep connections between Earth and the universe. Check out my video on why Earth's magnetic field is weakening. The processes we've discussed tonight are directly connected to that phenomenon in ways that will surprise you. Tonight, when you look up at the moon, you'll see it with new eyes, not as a static companion, but as a traveler on an epic journey through space and time, carrying with it the story of our planet's past and the seeds of its distant future.